Derivatives are very important in mathematics, in science, and in engineering. A derivative represents a rate of change of some kind of function, but it could also represent the rate of change of water flowing out of a bucket, through a hole in a tank, something like this. So it helps us measure these rates of change and model situations in which there's a rate of change. So if you're interested in that, stay tuned. We're going to introduce derivatives and several rules for calculating basic derivatives of simple functions. All right, let's get into this. So what I have here in this Mathematica tutorial is an image of a cubic function and a line segment. Okay, so if I wanted to measure the slope of this function in blue at a particular point, say when x is equal to 2, I'll move this over so you can see, right, such as here. Well, if I go forward a certain distance and measure the slope of a secant, right, from this point to this point, well, then you might consider that to be an approximation of the slope of the function at this point here that I'm circling with my mouse. Okay, now what we want to do is decrease this distance so that this line segment is more like a tangent line at this particular point. Okay, so that's the whole idea with the definition of a derivative. But I'm going to walk you through these Mathematica calculations, how we get this picture step by step. Okay, so what I have here is a plot of the function. It's a cubic function, as you see, from -3 to 4. And then what I've set out is h is equal to 1.25. So this is the distance I want to step forward with my secant to make this line segment, and we call this a forward difference. Now this point P is what I get when I replace the x value with 2. So I'm subbing in 2 and I get a corresponding y value. That is output right here, the 0.25, and that is this point right here that I'm circling with my mouse. Okay, next I sub in x is equal to 2 plus h. All right, when x is 2 and h is 1.25, then what I'm subbing in here is 3.25 for x, and then I get the corresponding y value on the function. Okay, so 3.25 and 26.328 is the y value. Next, what I do is I draw a line segment from P to Q. All right, and finally I show the two of those together and I get this nice little picture right here. Okay, so let's reduce the value of h. So we pull in the x, the second x point closer to the first one. All right, so let's take this down to 0.5. Shift enter, and we'll see what we get. You see, this is 2.5 now and 10.625, and you can see here that our line segment is smaller. Okay, so this is coming closer to this point, and it's getting more and more like a tangent line. Okay, so if we reduce this even more, 0.25, shift enter, let's have another look. Okay, it's right here in black, you can barely see it, but it's just about the same as a tangent line at the point 2, 5. All right, so you get the idea that when you make this closer and closer by reducing h, the step size, to 0, you will get exactly a very short, infinitesimally small line segment whose slope is equal to that of the function at the point you're interested in. In other words, a tangent line with slope equal to that of the function. Okay, so this is the basic idea behind the definition of the first derivative by limits. Okay, so let's come down here and write the definition. So we'll say f dash x in Newton's notation is equal to, and that is a limit. So I'm just writing here in comment form. Okay, I'm not intending to execute this. The limit as h goes to 0. And then I'm taking a limit of a fraction. So I'm going to open up a palette, Basic Math Assistant, move this over so you can see it, and I'm just pulling up this fraction. Then I'm going to close it. Okay, and you can see that the way I've written it out is put this in the numerator, so I don't want that there. So I'll just put something else there for now. And I'm just writing a comment, so this is not something I'm going to execute. Okay, so in the denominator, I want x plus h for the second x point, and then minus x. So I'm doing just rise over run here to talk about the slope of that secant. Right, in the numerator, I want f of x plus h minus f of x. So what I have here in this fraction is rise over run. Okay, so the rise is the second y point, which is this one I've got highlighted, minus the first y point, which is this f of x that I've got highlighted now. And then in the denominator, we have the run. So this is the second x point I have highlighted now. And then the first x point I have highlighted is just x. All right, now let's simplify this. Control C, Control V. Okay, in the denominator, notice that the x's vanish. So this is just x. Sorry, just h. Okay, in the numerator, I have f of x plus h minus f of x. All right, so this is a definition of the first derivative. Okay, it is also what we call the forward difference approximation in numerical analysis for the first derivative. Okay, but in that case, you would have h being some positive number. Okay, whereas here we are taking h to be so small that it actually becomes the first derivative of the function, or the slope of the function at the point xy. Okay, so let's use this to generate some rules. Okay, so let's scroll down and have a look at our first rule. Now this should say f of x equals ax to the n. All right, if we take the derivative, first derivative of ax to the n, we will get n times a times x to the n minus 1, where a is a constant. Okay, so let's use this definition here of limits to generate that rule. All right, so we say, again in comment form, if f of x is equal to a times x to the power of n, then let's have a look at our limit. We will use this definition, so copy and paste. Okay, now I'll copy this because I want to put here f of x plus h. All right, so what I do is I take the x and I replace it with x plus h. All right, and then this f of x is just a times x to the n. Okay, so this is applying the definition to the first derivative. Okay, now what we do is we simplify this. Okay, so I'll come down here and simplify this. Now notice this has an a and this has an a, so I can factorize that out of the expression. Let's do so now. Okay, I factorized it out. And next, I want to expand this. All right, so if I were to expand this using the binomial theorem, binomial expansion, you could also do this with Pascal's triangle. Okay, so when we expand this, now let's see if I can do this in Mathematica. So I need to clear the value of h because that we set in memory earlier. Okay, that's now cleared, and then I'm going to copy this, Control C, Control V, and see what happens when I just expand that. Well, nothing, but we know that the binomial function should work here. So n choose 1 okay, is n, and then n choose 2 is 1/2 n times n minus 1. Okay, so these are coefficients in the expansion of this. So for example, if I put a 3 here and I say cube, well, this is 3 choose 1, this is 3 choose 2, and this is 3 choose 3, the 1 in front of the x cubed there. Okay, so if I were to expand this, well, what I would have, okay, I'll come down to a new line, and we'll say that what we have here is x to the n, and then the next one is n choose 1 times x to the power of n minus 1 times h to the power of 1, and then the next one is binomial n2 times x to the power of n minus 2 times h squared, and then we'll say plus dot 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 plus, and then the last one is h to the power of n. Okay, now let's simplify these. So binomial, we've got these here, that's n. Okay, so this one is n. This one here is what we found down here, which we can just put in. Okay, and then and so on. All right, all the way down. Okay, now we want to simplify this. Okay, so I'll copy this, come down here to a new line. All right, notice that this matches this. Okay, so those two vanish, so we can get rid of those. And then what do we have remaining? We have a whole bunch of summands that all have the letter h in them here. So h squared, coefficient of the next one will be something times, well, I mean, it'll have a h cubed in it, and h to the 4th and h to the so on until you get to h to the power of n, which is the last term. Okay, so we can factorize out at this point. We can factorize h out. Okay, so I'll copy this, come down, paste, and I'll pull out the h. All right, so we took it out of there, we took 1 out of this, and then this last one will be to the power of n minus 1. Okay, all right, now notice we have a 1 on h and a h, and so these can cancel. Control C, Control V. All right, so I'm going to cancel that h. And then what do we have left over? We have several terms that all have a h in them there, but this one doesn't. Okay, so now what we're going to do is substitute in the value h going to 0. All right, we're taking the limit at this point. So copy this again, come down here, and now I'm going to take the limit, so I don't need this anymore, and then this will be plus 0 because I'm subbing in 0 there. Okay, and then what we have when we simplify this is just a times n times x to the power of n minus 1. Right, now this is what the rule said there, that the first derivative is n times a times x to the power of n minus 1. Okay, and we derive this using the definition of the first derivative by limits. Okay, so I'll move this out of the way now and I'll tell you some of the other rules. So if we have a function that is just a constant, its first derivative is 0. Okay, now you can do that in the same way using limits. It's fairly easy. Okay, third rule. If we have a function which is the sum of two functions, the first derivative of f is the sum of the first derivatives of each of the two functions. Okay, rule number 4. If we have a function f of x and it's a times g of x, where g is another function and a is a constant, well then the first derivative is just a times the first derivative of g. Now this one is really easy to derive using the limit formula for the first derivative, because you just factorize the a out of the expression and you get this straight away. Okay, now the next rule, number 5, is that the first derivative of sine of x is cos of x. That's one that you should memorize. Now, how do you derive this using the limit definition? Well, in the numerator you would have sine of x plus h minus sine of x. In the denominator you would have h, and you would have to take this limit as h goes to 0. Okay, to do that you would need what we call the angle addition formula and probably some special formula for the limit of sine of h over h, right? Which is a little bit more complicated. Okay, next rule. The first derivative of cos of x is minus sine of x. Okay, again, remember that one, very important. Rule number 7, the derivative of e to the power of x is e to the power of x. Very easy to remember, and you should remember that one. Last rule that we have here is that the natural log of x, when you take the derivative of that, you get 1 over x. Okay, so let's have a look at some examples. And I'm going to open up Mathematica again because I can show you how you can check your work in Mathematica. So what we have here is f of x is 3x squared. So if we apply the first rule, then the first derivative is 3 times 2 is 6 times x to the power of 1, because 2 minus 1 is 1. Okay, now let's check this in Mathematica. And incidentally, you can also do this in Wolfram Alpha. So derivative of 3x squared, and then with respect to x, shift enter, and we see down here we get 6x. Okay, very easy. All right, let's try that with this function. 3x squared plus cos of x plus 4. Now, oh, whoops, 4 goes outside. Now, you can use several of the rules that we have above to do this. So we have already calculated the derivative of 3x squared and found that that was 6x. The derivative of cos of x from rule number 6 is minus sine of x. And the derivative of a constant is 0. All right, and notice that we have the sum of 3 functions, so we can apply the probably third rule. We can apply the third rule, this one here, and say that that is the sum of the derivatives. Okay, so I can tell you what this is going to be before I press shift enter, so I'll make a comment and say that this is going to be 6x minus sine of x plus 0. Okay, now to check that, shift enter, and there we have it. That agrees with what the rules gave us. Okay, that's our second example. Let's scroll down and see what else we find. Okay, here I am talking about Leibniz's notation. So Leibniz's notation is very useful for talking about and calculating derivatives, because we have a symbol here that looks like a fraction. And that's no coincidence, because they act very much like fractions. Right, where you might expect a cancellation in a fraction, often there is a corresponding rule for derivatives that will do something similar. Okay, so this notation is very useful, and I suggest that you use it. The first derivative is also dy on dx, so that's the first derivative of y with respect to x, or in this case df on dx for the first derivative of f with respect to x. All right, scrolling down, let's look at this other example. So here we have an example showing all of the steps in the calculation of the first derivative of this cubic function. Okay, using Leibniz's symbols. So we apply this differential operator to the cubic function. Okay, and the rules say that we can separate this into the sum of these 3 derivatives. Okay, and then when we simplify each, the 4 can come through the symbol by the rules. And so we can simplify this first one as 4 times the derivative of x cubed plus 7 times the derivative of x minus 11 times the derivative of 1. Okay, and then we can simplify each of these, and then we find that we get 12x squared plus 7. All right, let's check this in Mathematica. All right, so I'm going to write d, and then with respect to x, and then I'll input 4x cubed plus 7x minus 11, shift enter, and it says 7 plus 12x squared. Okay, obviously that's the same as 12x squared plus 7. All right, so that's basic derivatives, and I'm going to sign off for now. I'll see you next time.